Hi, good afternoon, everyone. It gives me immense pleasure to introduce the first speaker in 2021's iMobile webinar series, Dr. Akhil Mathur. Dr. Mathur is the principal research scientist at Nokia Bell Labs, and he's based out of Cambridge, UK. He is also a member of the ACM Future of Computing Academy. Dr. Mathur's research interest lies in embedded systems, embedded machine learning and mobile systems, and he particularly focuses on scalability and generalizability of machine learning on the edge. Dr. Mathur holds a PhD from University College London, again in computer science, a master's from University of Toronto, and a BTech from DAIICT, where he was awarded the President's Gold Medal. Dr. Mathur has co-authored over 50 publications and has filed over 20 patents. He serves on the editorial board of Invert, which is the journal version of Ubicom that many of you are aware of. And he is in a committee of several mobile and sensing system conferences. His research has been covered by several media organizations. And with all the SIGMobile venues, I believe Dr. Mathur has published in almost all of them, and his work has been highly cited in various such venues. Okay, with that brief introduction, I'll hand over the stage to Dr. Mathur, who will continue with his talk.
Great. Thank you very much, Shogato, for inviting me, and also the iMobile team for having me here. I'm quite honored to be the speaker, and looking forward to your feedback on my research. So let me start by sharing my slides. Great. Okay, so today, basically, I'm going to talk about our research around sensory AI systems, and I will particularly focus on the challenges related to multiplicity when we design such systems. But before I sort of go into the technical details of our research, I would briefly like to sort of introduce our team in Cambridge and also tell you something about our research agenda over the last few years. And hopefully that will give you some insights and some context around the research that we have been doing. So we are called the Pervasive Systems team at the Nokia Bell Labs, Cambridge. This is a picture of the team on the right when we used to have summer interns in 2019. We haven't had summer interns due to the pandemic in the last year, but hopefully we'll resume again. And broadly, sort of our research focus could be summarized as end-to-end mobile and wearable systems. And as you can imagine, like this is a very vast area of research, and it involves, for instance, coming up with novel sensor devices, new forms of sensing algorithms to process the data that we obtain from these devices, then looking at several system issues that arise when we deploy these sensing algorithms on these new kind of sensor devices. We also heavily look into embedded machine learning, which is A, how do you process the sensor data using machine learning models? And B, how do you deploy these machine learning models on mobile and wearable devices? In the past, we've also looked at developing both personal scale and crowd scale sensing applications on top of these devices and data. And as you can imagine, again, it's a very wide area, and we have been lucky to have researchers with this diverse interests, and through collaborations internally, as well as externally with our academic colleagues, we've managed to accomplish a lot of interesting research in these areas. So just to give you some examples of the research that we have done, a couple of years back, we actually launched this platform called eSense, which is one of the first open hearable platforms for research. So this was like a dual mode Bluetooth hearable, which had like several embedded sensors, and we actually developed the firmware and APIs to support configuration and development of sensing applications to top of it. This earbud was actually made sort of public, and it was donated to more than 70 research groups around the world. Several of them were also in India. And we have seen a lot of community involvement with this project. Right now, we are actually working on the version 2 of this hearables, which has more advanced sensing capabilities. So if you're interested in this line of work, just keep an eye on our website, esense.io. And hopefully in the later half of the year, we will have more updates about the next version of the hearable. So in addition to creating these novel sensing devices, we have also looked at just personal scale sensing algorithms. For instance, leveraging the Wi-Fi signals emitting from your smartphones to detect face-to-face interactions between people. In addition to personal scale sensing, we have also looked at sort of enterprise or workplace level sensing, where we deployed both mobile and environmental sensors in a workplace to understand different aspects of workplace dynamics and give feedback to the users. These kind of systems were deployed in our offices in multiple countries, and we did like this longitudinal deployments over several years. We also managed to take some of our research outside. So instead of just deploying it in our offices, we actually deployed it at Web Summit, which is one of the largest tech conferences on the planet. Web Summit is not your academic conference, but it's like a conference where entrepreneurs and investors sort of meet with each other for business ideas and funding, etc. And it has more than 40,000 attendees every year. And with Web Summit, we actually developed wearable badges, like employee badges, but they had Wi-Fi sensing enabled in them. And so we deployed these wearable badges and some sort of Wi-Fi gateways in the Web Summit campus. And based on that, we offered like people analytics and space analytics services to Web Summit. And at this time, sort of around 2015, 2016, we realized that, machine learning and especially deep learning models are becoming more prominent in the community and especially are being deployed for mobile sensing and mobile systems. However, at the time, we also realized that it is incredibly difficult to actually take these cloud scale deep learning models and compress them and execute them on very small form factor devices like mobile and wearables. So this was sort of the core foundation for some of our embedded machine learning projects, such as DeepX and DeepI, where we looked at compression and resource shaping techniques to squeeze these cloud scale models to small devices. So this was like some of the early works in the mobile systems community around model compression and embedded deep learning. But thankfully, like now a lot of these techniques are quite commodity, and with like 5 or 10 lines of code, people can simply import them in their training pipelines. And basically, these are now part of frameworks like TensorFlow and PyTorch. So at this stage, we started asking ourselves, okay, what's the next big challenge in design of sensory AI systems? And I would like to argue that the next big wave of research opportunities in this space will come from when we address the multiplicity angle. And by multiplicity, I mean different forms of multiplicity, things like when AI will be deployed in multiple device settings, when these kind of AI and machine learning models have to deal with multimodality, as well as when we have to execute multiple models together on the same device. And let me elaborate on each of these aspects in more detail. So let's look at the multi-device aspect first. This is sort of a plot. This is a figure which shows the number of connected devices per person on average and how it has progressed over the years. So for example, in 1995, on an average, you would have less than one connected device with you. Fast forward to 2020 and people have almost 6 connected devices on them, either on them or near them, like things like Alexa or Amazon Echo. And it is projected that by the year 2030, we will have even more number of connected devices around us. And this is quite exciting because now we can rethink how we design sensor AI systems by leveraging the benefit of this multiplicity that is enabled by these many connected devices around us. The second aspect that I talked about is multimodality. So today, again, if you look at many of the sensor-based machine learning systems, they are sort of single device and single modality. For instance, it could be an audio sensing system running on your smartphone or a motion sensing system running on your smartwatch. But I would like to argue that in the future, we will move to this paradigm where we have multiple devices and multiple modalities. And it will be very interesting to rethink how we train machine learning models in this multi-device, multimodality setting, and also what level of system support do we need to cater to these scenarios. The third challenge that I think will come up will be about supporting multi-tenancy of AI models on edge devices. So it just means that right now we are at a stage where we can reliably run, let's say, one deep learning model on these small form factor devices. But in the future, if we have to support the execution of 5 or 10 machine learning models on these devices, what kind of challenges come up? So in the rest of my talk, I will touch briefly on these aspects about multiplicity, and I will tell you the research challenges that we see and we have encountered. and sort of what are the challenges left, what is the future, etc. So let me start with the first challenge, and that is the challenge of device heterogeneity. So as I mentioned, like this multiplicity in devices is quite exciting, and it gives us opportunity to deploy our mobile sensing applications on millions of devices around the world. But the challenge there is that different devices have different sensor hardware and software stacks. And because of these variations in the software and hardware stacks, these variations actually lead to variability in the sensor data that we get from these devices. Now, although these variations are quite subtle, but they are still computationally so significant that previous research has shown that you can use these variations to actually fingerprint a user based on their sensor signature. So the question for us now is that, are these variations really, critical for machine learning models? Aren't the deep learning models of today so robust that, they can just ignore all these variations and still give us very high performance? So to answer this question, we started looking at the challenge of heterogeneity in the context of audio models. And this was sort of our experimental paradigm. So we took 3 off-the-shelf microphones, namely ReSpeaker, Matrix Voice, and Plug USB. These are examples of microphone arrays that you commonly see in devices like Amazon Echo, and also single channel microphones that we would use with things like Raspberry Pi, or like very cheap microphones that cost $2 or something. So we took these microphones, and our goal was to actually see if there is an impact of the nature of a microphone on the performance of a machine learning model. So we took these microphones and we recorded data on these microphones simultaneously. So to do that, we basically took a public speech data set like speech commands or Libri speech, and we replayed this data set on a high quality speaker. And while the data set was playing on the speaker, we recorded on all these 3 microphones simultaneously. And by doing that, we actually created these microphone specific versions of the data set. So there was a matrix data set, a ReSpeaker data set, and a plug USB data set. We collected, of course, both training and the test data. And once we had the data collection done, we trained sort of deep learning models on each of these individual microphones. And so the first case study that we did was with a keyword detection task. So a keyword detection task is quite simple. You speak a keyword like "Hey Siri" or "Hey Alexa" into a microphone, and the machine learning model is supposed to infer what was the keyword. But the interesting thing we did was we trained this keyword detection model on the data that we collected from the matrix microphone. So the first row here. And then we deployed this, and we tested this model on both matrix and ReSpeaker microphones, the 2 green bars that you see. And the interesting observation was that, on the matrix microphone, we got an accuracy of about 80% for a 30 class classification. But when we deployed the same model on ReSpeaker, there was almost a 20% drop in test accuracy due to microphone variability. Now, I again want to re-emphasize the point that the test data in both these microphones had exactly the same content. The only difference was that it was collected on two different microphones. So just by the change of a simple microphone, we observed like this massive drop in test accuracy. Now, there was some concerns that maybe our models are not state of the art. Maybe we did not train with enough data. So we redid this experiment with cloud scale models that you see in Google and Microsoft offerings. And we tested it with the automatic speech recognition task. So again, the goal of automatic speech recognition is that you pass it an audio spectrogram, and the model is supposed to give you the transcript of the audio. And we deployed this thing with, again, a Google ASR model, which is hosted on the Google Cloud Service, and you can query it using the APIs provided by them, and also a Bing ASR model, which was provided by Microsoft. And we observed a very similar behavior that for different microphones, these state-of-the-art models, which were trained with thousands of hours of data, were giving us very different accuracies. So there was variability across different microphones. Some were very poor. Some had very, very high error rates. Some had slightly lower error rates. But the important point was that different microphones had massive variability in the error rates that we were supporting. And if we just look at the absolute increase in the error rate due to this microphone variability, we may see that the absolute increase is quite small, maybe 4% to 10%. But if you actually if you put it in context, the deep learning community has actually reduced the error rate in the last 5 years by just 10%, with all these advancements in the deep learning techniques. So if just by changing the microphone, we can nullify like a lot of these advancements, then it's a major problem for us and major problem for machine learning on mobile and wearable devices. So moving forward, like what is causing this? So technically, this problem is known as domain shift, and it basically attacks at the heart of supervised machine learning. So in supervised machine learning, there is a fundamental assumption that training and test samples must be drawn from the same data distribution. And if this assumption is not met, this is a phenomenon known as domain shift, and it can degrade the performance of supervised machine learning models. And we found that this is exactly what's happening in our case, because before this audio signal that I highlight in the figure, before it reaches the audio model, it actually undergoes a number of processing steps. So firstly, for instance, the audio signal encounters the acoustic sensor in the microphone, which again, previous research has shown that it can add its own variability to the data. Then this data is processed by some signal processing algorithms, which do maybe noise filtering or beamforming or other forms of signal processing on the data. And that add another form of variability to the data because different manufacturers can have different signal processing algorithms. So the key takeaway is that even before the machine learning, even before the data reaches the machine learning model, there are these various processing stages which add variability in the data. And if these processing stages are not the same between training and test stages, then this kind of assumption of supervised learning no longer holds, and we start seeing these accuracy drops. And again, just a visualization of the same phenomenon, we actually collected a 4-second speech segment in an anechoic chamber on these 3 devices that I mentioned earlier. So it's again exactly the same speech segment, and we can see that in the spectrograms broadly they look very similar, which is a good sign that it's fairly similar speech segment. But when we look at a minute level, there are some differences in the spectrograms that we observed in the last 2 figures. And we believe that these are these minute differences that are causing the machine learning models to fail on this data. So what is our solution? So our solution firstly is called mic to mic, and the key intuition is as follows. So let's say we have this training domain, which is a smartphone, and a test domain, which is a smartwatch. Right? Both have their own microphones, and we want to train a model on a smartphone and deploy on a smartwatch. Now, in the sort of vanilla setting where we don't have our solution, then what we will do is you will have this model trained on smartphone. We will pass the smartwatch data to it, and we will get some inference performance. And as I showed, this will have some accuracy degradation. But what the intuition is that what if we can have, let's say, some component which we call a domain translator, and what it does is it takes the smartwatch data and it translates or massages the data in a way that it starts appearing similar to a smartphone data. And if we can actually have this domain translator working very accurately, then this translated data could be then fed into the machine learning model, and we can have much higher accuracies. So then the research question becomes, how do you actually learn this translation function between a training domain and a test domain? And of course, we would like to learn this function using unlabeled data because collecting labeled data could be very expensive. So one way to learn this translation function is if we can, take these microphones in a controlled environment and collect perfectly time-aligned paired data from them, and then we can do some form of calibration between the microphones. However, collecting this paired data in a controlled environment could be expensive, and it's not very scalable. So the research question we asked was, can we actually learn this mapping or translation using unpaired data collected from the 2 microphones? Our solution was sort of revolved around the cycle GAN architecture that was proposed for computer vision tasks. And I won't go into the details here, but the high-level insight behind the cycle GAN architecture is that even though we do not have any paired supervision between the 2 microphones, if we actually do like a translation from A to B and do a reverse translation from B to A, then if both these translation components are very accurate, then we should arrive at the same signal after this entire cycle. So we can actually basically optimize this so-called cycle consistency loss. And by optimizing this loss over a period of, over lots of data and lots of epochs, we can accurately train these two generator components, which can take data from domain A and convert to domain B. If you're interested in more implementation details and the math behind it, please refer to our paper for more details. I will quickly jump to some of the results that we got. So in this figure, basically, let's say the figure on the left, I'm showing a performance when our training device was a re-speaker microphone, and we tried on different test devices. So if you just look at the red bars, so the first red bar basically shows that when we train the model on re-speaker and deploy it on re-speaker, we got about slightly higher than 80% accuracy. When we deploy this exact same model on matrix, we saw a 15% accuracy drop. And then we had several baselines related to speech enhancement and static calibration. They gave us some gains, but this approach that we proposed, mic to mic, that had the highest gains, and it was able to sort of recover almost 86% of accuracy in this case. And we observed this phenomenon across different microphone pairs and across different data sets. Of course, the performance was different depending on the data set and the microphone pair, but broadly we saw that mic to mic was able to address this problem to a great extent. We also tried to see if adding more microphones in the training process. Sorry, is there a question? Okay, I assume not. So,
folks who are not presenting, can you please put yourself on mute?
Okay, thank you, Amit. I will just continue. And if there are questions, I can take them later. We also try to do this experiment with multiple microphones, which means we train the model on not just one microphone, but on multiple microphones. So in this case, we trained on re-speaker and USB microphone and tested on matrix, let's say. And broadly, we observed similar phenomenon. The accuracy drops in this case was slightly smaller, but there was still an accuracy drop, and mic to mic was able to recover a large portion of this accuracy drop. Another important question in this setting is that how much data do we need to train these kind of translation models? And to do that, again, we varied the amount of unlabeled data that we use for this training. And then we computed the downstream accuracy that we get with different amounts of training data. And roughly we found that between 20 to 25 minutes of training data was sufficient to learn this translation function. And after that, the accuracy sort of plateaued and we did not have any further gains. So yeah, anyway, I think this was the first problem that I wanted to mention, that when we go into this multi-device setting, we will have this massive heterogeneity in our devices. And this is something we have to take into account for sensory AI systems to be accurate and robust. Let me see if there are any questions at this stage. I can answer them, otherwise I will just move on. Shogata, are there any questions?
Yeah, there are a couple of questions, Akhil. First one is for your data set, did you do any pre-processing on this data set?
Yes, so basically we did, so we obtained the data set directly from the microphones, and then we did basic pre-processing, like normalizing the data, or if, for instance, MFCC features were used, so MFCC normalization, etc., like very standard techniques that are used in audio processing. So that level of pre-processing was done. But other than that, I know there are things like data augmentations that are done quite a lot to make these models more robust. We did not try them here, but we only did basic signal processing on the data.
Another question is, usually the variations that you observe are due to certain hardware level non-linearities. The question is, can we learn these non-linearities or map them? Is it possible to do the mapping?
Yeah, that's a very good question, and that's something that when we were trying to do this, one of the baselines was this hardware calibrating these microphones in a controlled environment. And we observed that these nonlinearities are maybe not that easy to calibrate in a controlled environment. So to answer this question, it's very hard to say whether we can do it, but the intuition there is that the data tells us quite a lot about it. And if we, and also like, I think from a machine learning perspective, like these low-level microphone hardware specific or software specific variations are completely hidden, right? So even if two microphones have these nonlinearities or some software variations, all we get at the end of this microphone processing is their processed output. So as a machine learning developer, all you can do is operate on the data that we get out of it, and then we try to see if, what is the potential of learning these translation functions. But I think the question is very valid that maybe these functions may not work on all forms of data. We have also tried them on, let's say, Wi-Fi data and tried to translate them across different rooms, let's say. So if you collect Wi-Fi data in one room and deploy it in another room, there is massive variability. And we tried to learn this translation function there, and we failed to do that because the variability was maybe too high in doing that. So it's still like heavily dataset dependent. There are like some first principles from a machine learning perspective that we have explored later on. But broadly to your question, like, yes, for microphones, it seems possible to learn these kind of variabilities, but it may not be possible for all forms of data sets or all forms of variabilities.
Take the third question that we have, and then you can carry on. So the third one is, would you call mic to mic a standard transfer learning problem?
So there are two ways to look at it. So in transfer learning, one way is that you adapt the parameters of the machine learning model itself. So your machine learning model, let's say, was trained for device A, and now you want to deploy it in device B. So you modify the parameters to fit the characteristics of device B. But in what we are saying is that in this case, you do not really have to touch the machine learning model at all. This translation component can be imported into the pre-processing pipeline. So if there is any domain shift that is observed, then you can import this translation component, and it does like massaging of your data at the pre-processing stage, and then feeds the pre-processed or translated data to your machine learning model. So in that sense, I mean, you can call it transfer learning, but it's sort of slightly different from the traditional transfer learning where you are actually adapting the model itself.
Yeah, I think you can carry on then.
Okay. If there are more questions, I can take it at the end.
Yeah. We can take it at the end. Then.
Yeah. Thanks. Okay. So the second problem I want to talk about is around efficiency in these multi-device AI systems. So as I mentioned, like when we have these multiple devices around us, it's in a way it's very nice because we have multiple observers for our physical phenomenon. So for instance, let's say we are doing some audio sensing. You may have multiple microphones around you, right? In your earbud, in your smartphone, in your home gateway, etc. And this kind of redundancy in sensor signals is useful in case one microphone stops functioning or gives us faulty data. Then we can leverage the other microphones to achieve our sensing task. We also see this form of redundancy in our physical activity recognition. When we are running or walking, we have smartphone, smartwatch, and potentially like a smart glass. All of them have IMU sensors in them, and we can leverage this form of redundancy to create accurate sensor AI systems. So one way to achieve this sort of multi-device systems is using sensor fusion. So we have sensor streams coming from these multiple devices. We can either fuse them at the input layer of a machine learning or deep learning model, or we can do late fusion at a feature level. The problem with like this, or one downside of these fusion approaches is that they make strong assumptions about the availability of devices. So they sort of assume that all the devices have to be available all the time for the fusion architecture to work seamlessly. I know there are some modifications, some improvements going on, but broadly, I think that is one assumption. Another big problem is that it demands significant system resources, because if we have to do sensor fusion, it means we have to sample and collect data from all the sensors all the time. And in some sense, we are doing redundant computations and draining our system resources. Another approach that has been explored in the past is about sensor selection. So, and that is done in a static way at training time. So when we are training these models, basically we look at which device gives us the highest average accuracy on some validation set. and then we choose that device as our primary device during deployment. So this approach is also not ideal because we have seen that in a real world, basically the performance of these different devices vary across time. So in this example, I'm plotting the results of a physical activity recognition task. On the y-axis are the F1 scores that we obtained for a, I think, 7-class classification. And the colors represent different devices. So, so basically for the first minute, we see that the blue color device had the highest accuracy, which means the smartphone gave you the highest accuracy in this case. And by the way, this was, I think, evaluated on one of the public data sets called real world data set. And then we see that, after 1 minute, if you look at the accuracies in the next minute, then maybe in this case, your smartwatch is giving you the highest accuracy. In the third minute, maybe a shoe mounted sensor is giving you the highest accuracy, things like that. So the core point is that the quality, which in this case means inference accuracy, that is varying across devices and over time. So having like a static view on and selecting like one device may not be the most optimal choice here. So the question that we want to ask is that, can we actually assess and compare the sensing quality of these devices at runtime? That is, can we select a device which is likely to provide us the best inference accuracy? And how it would look like in practice is as follows. So let's say we have these 3 candidate devices, D1, D2, D3, each of them having their own machine learning model. What we want to do is, let's say we have a very short assessment window where we take the sensor streams from all these 3 devices, and we do this assessment that which of these devices has the highest quality. Let's say we select D2 as the device. And at this stage, what we will do is turn off sensing on D1 and D3 and save the energy resources there. And for the next few seconds or next few minutes, we will complete sensing and inference only on D2. And then again, after this duty cycle, we will repeat the assessment process, and maybe a different device will come up as the best device. And again, we will turn off all of the sensor devices. So by doing that, an obvious benefit is that you can save resources in sensing and machine learning inference. And the question really here becomes that, how do you define this quality function? How do you do this quality assessment? So we tried like a couple of different approaches to do that. One was a heuristic-based quality assessment, where we leverage the confidence values that we get from machine learning classifiers as a proxy for quality. So just as an example, when we, let's say, use a neural network, the output layer of a neural network gives you, let's say, softmax probabilities, and we can use them as a measure of confidence of the classifier, let's say. In practice, however, these probabilities are not very well calibrated, so we have to do some math to calibrate the probabilities. But the general idea is that we can somehow use this output probabilities as confidence values. And for that, we tried like different approaches. So here, I think if you look at the table at the bottom, let's say we have 2 devices, a phone and a watch, and we were doing a 4-class classification. So the 4 classes were running, walking, standing, and sitting. Let's say we pass the data from the phone and to the machine learning model, and we get these 4 probabilities for the classes. And from the watch, we get the 4 at the bottom. So we can sort of apply different strategies. One strategy could be that whichever device gives us the highest confidence, we can choose that as our highest quality device. So in this case, phone has a highest confidence of 0.7 and watch has 0.65. So we can choose phone as the device and turn off the watch. We can also look at margin sampling based approaches, where we take the difference between the top 2 class predictions and choose the device accordingly. Or we can look at whichever device has the least entropy, and we can choose that as our high quality device. So this is like a heuristic based approach to do this quality assessment. We also tried like learning based approaches, and there the idea was that, can you actually learn this quality function again using a neural network? So the idea was that we pass, let's say, all these sensor streams to a neural network during the assessment time, and the network should be able to tell us which sensors are high quality and which sensors are low quality. One downside of this was that we had to come up with this so-called quality ground truth, which tells the neural network how to do supervised learning. There are more details about how to come up with a quality ground truth in the paper if you're interested. But again, broadly, the idea was that given this quality assessment function in the form of neural network, we pass different sensor streams to it, and the model will tell us which sensor streams are high quality and which are low quality. And to do this kind of training, we use the CME's neural network architecture, which is commonly used for image ranking and image comparison tasks. And we showed that you can repurpose it for this kind of quality assessment of different sensors. So let me provide some results about the performance that we get on a human activity recognition task for both opportunity dataset and the real world HAR dataset. So in this figure, basically, I'm showing F1 score on the using the bar charts, and the line chart shows the total energy consumption of different approaches. So let's first compare HQ and LQA are our proposed approaches. One is heuristic based and one is learning based. And the two baselines let's look at right now are a fusion baseline, where we just fuse all the sensors, and a voting baseline, where we take majority voting across the inferences from all the devices. So, so the first observation is that our approach basically gave slightly less accuracy than the fusion approach for both the data sets, about 1% less, but it had higher accuracy on the voting than the majority voting in the case of opportunity data set, and slightly similar in the case of real world data set. However, when we look at the energy footprint, the energy footprint of our approach showed by the line graph was much smaller as compared to the fusion and voting approaches, and it sort of decreases. It's inversely proportional to the number of devices we have, because as the number of devices increase, the fusion takes more and more energy. But however, our approach, because it does like a single device based inference, it always has quite a static energy requirement. We also compare it to a single device setting, where if you just run inference on a single device, what are the accuracies and the energy there? And again, we see that there is a massive accuracy gain if we apply this quality-based assessment compared to single device-based learning. However, of course, this thing comes at a cost of some energy cost, because we have to run this assessment function, this quality assessment every few seconds, and that adds some energy cost to it. So, depending on the kind of requirements we have in our application, we can decide whether to go with fusion approaches or this quality assessment approaches. If we are okay with slightly less accuracies, but we are very particular about energy, then maybe the single devices approaches are also fine. So to conclude sort of this part of the talk, the main point I want to make is that this redundancy in sensor data is useful, it's important, but it also comes at a cost from a systems perspective. So just because it's something gives us very high accuracy, it doesn't mean we should always use it. I mean, we should look at like other aspects like energy and system resources also. Okay, so in the interest of time, I will quickly move to the third challenge, which is about supporting the execution of multiple AI models on the edge. And today, the support for this kind of multi-tenancy on the edge is quite poor, in my opinion, and there is a lot of room for research in this space. So let's look at what are the challenges in machine learning deployment on the edge today. Firstly, I think there is very poor support for multi-tenancy of machine learning models on edge devices today. And you may ask, why is multi-tenancy important? So as an example, let's think about a traffic camera deployed on a traffic junction. And this camera is probably supposed to do multiple inference tasks, like for instance, number plate recognition, detecting speeding or traffic violations or other forms of suspicious behavior. And all of them could potentially be achieved by running a machine learning model. So in that case, multi-tenancy will become a key component of future edge systems, especially those which are AI enabled. And today, deploying these multiple models is quite complicated. The reason being that different machine learning models have different sort of library requirements or dependencies. So some run on TensorFlow 1.0, some run on TensorFlow 2.0, and there are massive conflicts between libraries, and it's quite difficult to deploy multiple models directly on the host OS. So we need some system level support to sort of guarantee this form of multi-tenancy without conflicting or affecting the performance of other models. Another issue today with machine learning deployment is that model developers need to write these very tightly coupled inference pipelines. So they need to, like, for instance, get data from the camera or underlying sensor. They need to have their pre-processing, they need to do their inference, and all of them is typically written by the machine learning model developer today. However, in this multi-tenancy setting, it's very likely that different models will share a lot of these components. For instance, maybe several of these vision models may have very similar pre-processing pipelines. And there is a lot of opportunity for sharing these operations across multiple models. And today, this level of support is quite sort of missing in many of the edge AI platforms. Another big problem is that these inference pipelines that we write today, they are not aware about the system state and what are the resources available. So for instance, again, on these kind of edge accelerators provided by NVIDIA and other companies, they may have a CPU, an embedded GPU, or a tensor processing unit. But if your model is not aware about all the system resources, it may not be able to give you the most optimal performance, or the most or the fastest inference time, for example. And in addition to that, I think another big problem is about energy awareness. Like, a lot of the machine learning pipelines are not aware about the energy resources on these devices. And that's particularly important for battery powered devices. Like if your phone or if your wearable device has just, let's say, 5% of the battery left, and your machine learning models go ahead with like some very expensive inference, it can completely drain the battery, right? So we need to have more energy awareness in these inference pipelines. So the solution that we are working towards right now is called SensiX. And sort of SensiX is a short form for sensory Unix. And working at Bell Labs, we want to add Unix into every of our project. So anyway, so SensiX, the goal of SensiX is to design this ultra efficient system layer, which can sit on top of the host operating system, which could be your usual Linux operating system or like FreeRTOS or CoreOS kind of embedded operating systems. And so it sits on the top of the host operating system and between the host OS and the machine learning developers, and provides like these provides the right abstraction for developers to do all this, to do away with all these system complexities. So there's a lot of information on the slide. I mean, I would say maybe if you can just focus on the red blocks here, or the brown blocks. So for instance, SensiX has the sensor processor component, and that takes care of interfacing with all the sensors available on the embedded device, and sampling data from them and feeding it to the machine learning model. And by doing that, really, the machine learning developer doesn't have to worry about if tomorrow somebody changes the camera on the device or a new microphone is installed on the device. So all those complexities are completely abstracted by SensiX. Then if there is, like, let's say, sensor redundancy, there are multiple sensors doing the same thing, then SensiX can do the sensor selection that I mentioned earlier and only pass the best sensor stream to the machine learning model. If we find out that there is some form of domain shift happening, then SensiX can automatically import this translation component that I talked about into the inference pipeline. SensiX also has this so-called energy reactive scheduler, where we constantly monitor the energy available on the device. And based on that, we do some optimizations either at the input layer, which means we can change the dimensionality of the input data, or we can add some form of early exits to the machine learning model to reduce its energy footprint. And finally, there's also like an execution runtime, which schedules the execution of these machine learning models across different hardware processors like CPU, GPU, or other AI accelerators. So broadly, I think the vision of this platform is that we want to make it as easy as possible for model developers to deploy their machine learning models on the edge. So today, the way it's so easy to deploy Android applications on a smartphone, we should be able to reach that level of abstractions and simplicity for model developers. SenseX is currently sort of a work in progress. We have some publications on it currently out, and some are still in the pipeline. So hopefully in the later half of the year, we'll have more details on how it works and how it gets incorporated in different edge devices. and I look forward to sharing them with the community later on. So with that, I think I will close, and I will like to acknowledge my collaborators in all these works, Anthony Saposu, Chulong Min, Alessandro Montanari, and Fahim Kausar from Nokia Bell Labs, Professor Nadia Barthus from University College London, and Professor Nick Lane from the University of Cambridge. And thank you very much. If there are any questions, I'm happy to take them.
Thanks, Akhil. That was a wonderful talk. There are a couple of questions. I'll just read them out for you. And if you have your chat open, you can look at that, like while I'm reading it out. So the first question, I think this is from the first part of your talk. Okay. The question is, the problem here is the variability of input data. Can we think about a standardization rather than looking into the ML handling?
Yeah, that's a very good point. Like, so we can look at, let's say, if there are if we can standardize the hardware sensors in some way, and then we can push for standardization of the signal processing algorithms that different manufacturers are using, that would do away with a lot of these variabilities in the data. There's a big question because the space of embedded hardware is growing very fast. People come up with IoT devices every day on their own, and there's like a lot of this build your own BYOD kind of movement going on. So I would say it may not be that feasible to have very massive standardization across this different hardware. And if we want to again make our machine learning model sort of future proof, in the future maybe someone will come up with a hardware that doesn't conform with the standardization, then we still need these kind of approaches potentially. But I think broadly the point is well made, that if we can solve all the complexities in the pre-processing pipelines, then we don't need a machine learning solution, at least to this extent.
Okay. The next one is, I think this is for the second part, for the incremental machine learning. What kind of algorithms used? Any kind of continuous learning algorithms? The second point is, should we really need deep learning for sensory data learning and prediction? Okay.
Yeah, the first question is good. I mean, so there are continual learning algorithms for when you have to add more classes, or when, for instance, when some classes start disappearing from your data. My team has explored them. I haven't worked on them directly, so I can't give you like a lot of technical details, but yes, continual learning algorithms for both increasing the label space, and if there is any change in the label space, or if there is any change in the feature space of the data, I think there are continual learning algorithms that people explore. The second point is interesting. Why do we need deep learning, right? So one answer is that everybody's doing it, so why not? But but that's a bit of a cheeky answer. But I think there are benefits in terms of accuracy that, I mean, we have seen the benefits, right? As opposed to the traditional feature-based learning where we manually extract the features. So, I mean, there are for sure accuracy benefits at the expense of energy and computational complexities. So I think rather than saying we should choose one or the other, we should look at, I mean, whatever gives us the best accuracy, but then also try to optimize it for mobile and wearable devices. So maybe the most state-of-the-art deep learning model is not needed for mobile and wearable sensing, but maybe we can compress the model. We can use a smaller architecture, because they are still giving us quite significant accuracy gains. And again, there are problems with generalizability even now, and that's something as a research challenge we can solve in the future. So I do see that there is for sure room to apply deep learning in sensory data.
Okay, the next one is, can you please share your views on sensor selection with multiple modalities? When selecting sensors, how can we ensure that we are not choosing some sensor which may be misleading us?
Yeah, that's an excellent question, and we actually thought about it. Like, for instance, let's say you want to fool your activity trackers that you are running. So all your device. I mean, if you just have one device, then all you can do is maybe make some motions with your wrist, and maybe potentially you can fool your tracker. But if you have multi-device, if you have like data coming from multiple devices, then at least from a fusion perspective, there is a greater chance that maybe all these devices may not agree with this faking behavior, right? Maybe you see a very static signals on all of the devices, and then some form of majority voting or building this behavior into the neural network, we can try to see if we can filter out this noisy behavior or malicious behavior. So from a fusion perspective, definitely, I think once we have multiple sensor streams, we can look at them, either fuse them, or we can do this kind of sensor selection based on to sort of weed out these erroneous sensors or like malicious sensors in a way. So I don't know if that answers the question, but I do see that it's a real problem, and sensor selection or fusion can actually target this problem.
Right, yeah, that can always be tricky, right? Yeah, so the next question is, does the SenseX framework is supported for Android OS? Because of Android is emerging in smartphone tablets, so does your platform support Android?
Yeah. So right now, no. Right now it supports, it's written on Python. And right now we are targeting devices like NVIDIA Jetson series devices and Raspberry Pis, where there is a good Python support. The next step obviously is to incorporate SenseX in some of the wearable devices that we ourselves are creating, like the earbuds that I showed in the beginning. They do not have enough computation power to run the full SenseX stack, but we may be able to run a miniature version of SenseX on these wearables and other embedded wearable platforms. So that's like one of the next steps. But talking about Android for sure, I think like a lot of the components that you see in SenseX are basically core algorithms. Right now they are implemented in Python, but there is no reason why they cannot be implemented in Java or in C or C++ for future platforms. So in short, like that's not on the agenda right now, but it's something we will look into once we have like the core framework working very robustly for Python-based devices.
Right. And the question is how multisensory processing with SenseX is compatible with wearable devices like smartwatches, smart glasses, etc.
Right. So the way SenseX thinks of sensors is that sensors are just sensors could be like connected physically to the edge device, or sensors could be remote, right? So in this case, your smartwatches or smart glasses could be connected to Bluetooth with the SenseX box. SenseX box is, let's say, it's some edge device, maybe like an NVIDIA Jetson or a Raspberry Pi. So, and these devices, of course, have Bluetooth and Wi-Fi interfaces, and your smartwatches and smartphones can connect to these devices on these interfaces and feed their sensor data to them. So from a systems perspective, we don't really differentiate whether the device is connected physically over a wire or it is wireless. We can support like all these different devices.
Yeah, I think that's all questions that I see on the chat, and yeah, there is definitely like what Shobhajit is saying. I'll echo that. This was really an excellent talk. I actually wanted to ask you one question myself, which is very different from the technical part of it. So this is more from the SIG mobile side of it. Okay, so like you are part of the Invert's editorial board, right? So like what suggestions or what observations have you seen for submissions from India? Okay, so and what suggestions do you have for people who are trying to publish in say Invert or any of the other SIG mobile vendors?
Yeah. So yeah, I think firstly, of course my answer would be biased based on the papers that I've reviewed. So it's no more like not really generalizable to all the submissions from India. But the things I've seen is that I think what Amit mentioned in the beginning, that there are some unique challenges that we have in India due to population density, due to infrastructure. And I'm seeing like, there are submissions coming out which are tackling these unique challenges. And that makes for very good mobile systems and sensing papers. So for sure, I think there is very good and interesting technical content coming out. Maybe one limitation I'm seeing is that I don't know if it's due to the sort of hype and exposure to machine learning today. Is like a lot of people are just focusing on accuracy as a metric and not evaluating their systems from other things that are of interest to the mobile systems community. So I'm seeing like the evaluation is basically we try this on 3-4 data sets, we report the accuracies, and and the other evaluation is really very, very shallow. So my advice would be really, if you are submitting to SIG mobile venue, especially Mobisys or Mbot, would be to make sure that you cater to the core interest of that venue. So for instance, these venues place a lot of emphasis on system evaluation, real world deployments. So talk about those things, go into detail of those things. Accuracy is always an important metric, but make sure that other things are equally well highlighted. And another thing I would say is, when we are writing these papers, let's say based in India, a lot of these challenges may be very familiar to us, right? So we do not give enough background to the reader about why this is a big challenge, or we just assume that everybody would know about these challenges. But it's always very important to have like a very detailed background or introduction section that sort of contextualizes or situates the work in the right context and explains why this is an important problem to solve in an Indian context, or etc. Again, maybe in the US, this problem is not existent, doesn't make sense. But if we can convince the reader or the reviewer that this is an important problem that I need to solve for India, then I think this makes for a good paper. Yeah.
Thanks. Yeah, that was a good insight. I think if you are okay with it, I'll suggest others, if you are interested, you can get in touch with Akhil if you have any further questions about any of the presentations, any of the details that he presented today, or if you would want any other information. It's Akhil,
sure, absolutely. Yeah. I recognize I did not give a lot of math and technical details. So if you have questions about those things, I'm happy to answer offline over email or over chat.
Thanks. I think that was an excellent session. Thank you. And Amit or Shandeep, any last words that you have?
Yeah, so thank you, Akhil, for this wonderful talk. I think the session was very lively. And finally, thanks to Shogato for organizing and coordinating the talk. Sami, anything to add?
No, I just echo the thanks, and it was a very topical session. I actually personally currently work on some cameras, which are also places where there are multiple models that are being run for computer vision related stuff, right? A lot of traffic related stuff or people recognition stuff. So this is a very real problem with a lot of practical use case. And there is a lot of work in industry as well that's going on in this, not in standardization per se, but building products. So yeah, thanks a lot, Akhil. This is fascinating work, and I guess we'll all stay in touch and people can ask questions regarding this, and hopefully we'll get more submissions from our community to your journal as well as to anything relevant.
Great. Thanks again for inviting me. It was really a good session, and thanks for the great questions. I think I really like the depth of the questions and the interaction there. Yeah, thank you again.
Thanks.
Thanks, everybody. So I think we are done. We'll now close the call.
Bye.
Bye-bye.
Bye.
Bye-bye.
Thank you very much.